can jump in to ask questions. The slides are just there to provide some grounds for discussion, so happy to be interrupted whenever.
Okay. Do you just want to check if you can share? I'm not sure if
Oh yeah. Sorry, give me 1 second. Does that work?
Yeah, that's great.
Great. I'm guessing this usually starts around 5 after.
Yeah, I normally wait a minute or two for any latecomers.
Okay. Well, in the meantime, if anyone does have any questions that you'd like me to discuss either now or later in my talk, happy to take them before we get started with the slides.
I had a question just about the model accuracy verification protocol. I'm not sure if I think I misunderstand one point in which we have the model provider in the situation where the model provider aborts.
Sorry, the model provider, what, sorry?
Is aborting. So it's on page 6 of your paper.
Right. This protocol is actually quite tricky. I actually need to check the details, but basically the model provider will abort if they don't think they're going to achieve the accuracy with the inputs. Actually, they can actually just deterministically determine this. And I believe if the model provider aborts, one of the model provider or consumer gets slashed.
The consumer is getting slashed.
Okay, yeah, so the consumer gets slashed. And the way that you prevent the malicious model providers is that you basically need a reputation. And if a model provider aborts too many times, then they can see that they're being malicious.
Okay, yeah. Okay.
And then in order for a model provider to participate in the marketplace at all, they need to stake some large amount.
So you also have this reputation system as well as
you actually
another
don't
variable.
Reputation system. You just need staking. But the reputation eases things over, and the reputation is just a record of whether or not the model provider aborted or not.
Okay, that makes sense. Okay, well, if you want to get started.
Yeah, sure. More than happy to get started. So as I mentioned, for the folks who weren't here earlier, I do have some slides, but feel free to interrupt me at any point in time if you have any questions. Happy to keep this interactive since it's a relatively small audience. So I'll go ahead and get started. So I'm Daniel. I'm currently I'm joining as an assistant faculty member at UIUC in the fall in the computer science department. And today I'll be talking about scaling trustless DNA inference with zkML and also some applications. So this is kind of the obligatory slide that you have at the start of every one of these talks, which is that ML is eating the world. And so, apparently ChatGPT was the fastest application to have over 100 million active users. And there are many other examples of ML, including, say, in search and also for generating images with Midjourney. As it turns out, this is the Midjourney logo. I didn't know this either. So the question that we'll focus on in this talk is, can we execute these ML models trustlessly? And I'll return to the question of why we care about this in a few slides. But just to emphasize, there's many ways to do trustless execution of computation. So you can use multi-party computation, homomorphic encryption, and zero-knowledge proofs. and also even trusted enclaves, which I don't have here on the slides. But what we're going to focus on in this talk are zero-knowledge proofs. So zero-knowledge proofs let a prover prove that a computation happened correctly. And in the case of an ML, ML is a program, so you can prove that the execution happened honestly. And then anyone can verify a proof once it's been produced. And in terms of the performance considerations, you can get privacy, a very specific form of privacy, and also validity. So even malicious provers can't forge proofs under standard cryptographic assumptions. You also don't need any interaction, but unfortunately, the compute overheads are quite high. And so in this talk, I'll describe how to compute efficient zero-knowledge proofs for ML algorithms and also for image edits. So just to be very explicit about what zero-knowledge proofs are, I'm going to use this notation throughout the talk, so I'm going to walk through it somewhat slowly, even though I'm sure a lot of people in this call are already familiar with this. So a prover can prove that a function f happened, the execution of f happened correctly with some private inputs and also some public inputs. And it'll produce this proof, which you can then send to anyone. And then given this proof, this verifier can verify that f ran correctly. I'm actually also missing that the verifier needs x, but that's not super important here. What's really important is that this w here is private. And a really nice feature of zero-knowledge proofs is that they can be computed on demand and after the fact. So at the start, there was a question about these protocols to prove model accuracy. And so unlike, say, multi-party computation, not everyone needs to be online for these proofs to happen. The first application I'll talk about are trustless audits. And then I'll talk about decentralized prompt marketplaces, and I'll finish with trustless biometric identification and also fighting deepfakes. And I'll start by discussing trustless audits. So first, why do we care? Well, with a trustless audit, you can prove statements, for example, that you ran a specific FDA-regulated model, or for example, that Twitter isn't messing with your timeline, for example, censoring tweets. And so as ML becomes more and more integrated into the systems we use on an everyday basis, it's going to become more and more important to audit these systems. So beyond that, ML service providers are proliferating. So I actually don't have it in these slides, but there have actually been some recent accusations that OpenAI has nerfed their GPT-4 model and is now serving a much cheaper model despite users paying the $20 per month. And so in this particular example here, I'm showing an example of a medical classification task, but you can also imagine a model consumer being a paying user of GPT-4 asking OpenAI, hey, are you really using the GPT-4 that I signed up for last month? And a model provider might either be hacked in the case of a medical model, or in the case of OpenAI, they might be cost-cutting and be serving cheaper models. And so this core challenge is how can we verify that a machine learning model was run? So today, you have to basically go off of what OpenAI says or what the model provider says. And so the model consumer has no recourse if once the model provider sends them the result of the inference. So one way to address this is to use these zero-knowledge proofs. I'm going to walk through in detail what this F is specifically for inference, because it'll actually change depending on the application. So if we take what I call the functional view of inference, we compute some forward function, given the weights and data, it'll produce an output. And here, this forward function basically encodes the model architecture, and the weights and data are inputs. So here, this forward function is the F. And for inference, what's public are commitments to weights, data, and output. And what's hidden are the weights and the data. In many circumstances, you want to make the output public, but again, it depends on the particular application at hand. And because you're committing to the weights, data, and output, the model provider because they can't forge a proof or the commitment, they're bound to running a specific model. And so, for example, in the OpenAI case, they can prove that they're actually producing results from the model that you paid for last month. Now, beyond that, there's many other parts of the machine learning pipeline, and one other important part is training. So one thing you might want to do is also prove that you train a model on a specific data set. And I'll also describe why we might care about this in a few slides. But the way this works is that in step one, you commit to the training data. And so here you compute commitments to the training data, and these commitments are typically hashes. And once you have these commitments to the training data, you then produce zk snarks of the training process. And the specific algorithm that I'm showing here is stochastic gradient descent, but you can also imagine using other training methods as well. So I mentioned that this F here changes depending on the application. So of course, it'll change for training as well. So if we go back to the functional view of inference, it's this forward function which takes in weights and data and produces the output. But for SGD, it's actually slightly different. For stochastic gradient descent, the inputs are weights and data, but the output are actually new weights. And so here the function f is not the same as for the inference. Now for SGD, what's made public are commitments to the weights and data, and what's made hidden are the weights and data themselves. And so what you see is basically that the model provider is doing the training process on a step-by-step basis using stochastic gradient descent, where you can confirm that the previous step, the next step was produced from the previous step by matching the commitments to the weights. And at the end of this process, you have some commitments to the weights at the end of the training procedure. So given these commitments, we can now perform what I'll call test time trustless audits. And here we can compute audit functions over data and weights. So here, these are the commitments are public and the weights are hidden. And I mentioned that we might want to perform audits over the training data as well. And you can prove statements of the form, the data isn't biased. So for example, that you're using a demographically balanced set of a demographically balanced training set for the case of a medical model. And you can also do things like the model performs well. Going back to the example that was asked at the start of this talk regarding the model accuracy procedure. And there are many other audits that can be run as well. For example, that Twitter isn't censoring your tweets or anything else of that form. So I walked through two specific instances of what F is for inference and training, and also this idea of audits. Before I move on to the next part of the talk, are there any questions up until now? Okay, well, if you have any questions, feel free. Oh, let's see. Yeah, so if you have any questions, feel free to leave them in the chat. Otherwise, I'm going to go ahead with the rest of the talk. But again, feel free to stop me at any point in time. Happy to keep this very interactive. So the next application I'll talk about are decentralized prompt marketplaces. So first, I'm going to walk through a little bit about generative AI. So if you look at generative AI, it requires these prompts. So what I'm showing here is an example of stable diffusion, and the output is an astronaut riding a horse, and the input is the prompt, an astronaut riding the horse. And so the generative AI takes in typically text or perhaps even other images as inputs, and outputs either text or other images. So in the case of GPT, in the GPT line of models, it produces text. In the case of stable diffusion, it produces these images. So one of the things about generative AI is that prompts are valuable and difficult. So for example, I'm showing here an output, well, on the left and right outputs of Midjourney. And on the left, I'm showing an example of an actual prompt that was used to generate this image. And as you can see, it's quite complex. You have to specify a whole bunch of things like cinematic, off-center, to shoot, 35mm film, still, 30-year-old French man, curly brown hair, and it goes on and on. And in order to produce these photorealistic images, you really need to have detailed prompts. So, you know, this example here that fooled people on Twitter for a while, this is the prompt that I came up with to generate something similar. Of course, it doesn't work because I'm not a good prompt engineer. And you might wonder, like, how much are these prompts actually worth? Well, this is a real news article. It's not fake news. These AI prompt engineer, these jobs can pay up to $335,000 a year and don't even require a background in tech. So, when people are saying to get these English degrees, maybe there is something to it. But beyond just Midjourney, there's also a whole host of other complex methods of prompting. So, for example, there have been some back and forth on whether or not GPT-4 can play chess. And as it turns out, if you prompt GPT-4 correctly, it can be on par with an old version of Stockfish, which is a very powerful chess engine, but it requires careful prompting. And if you just do the naive thing of just give it a list of chess moves, it'll do very poorly. And so there is something to this prompt engineering, despite this somewhat ridiculous number. So because these prompts are very expensive, you might want to be able to purchase these prompts. And so one thing you can do is produce a proof of prompt. And the way this works is that you goes back to the inference. So you take in a prompt, and then you produce a zk-snark of the output. Now you are doing inference in a prompt marketplace, but the prompt marketplace is slightly different. I'm assuming you're using public models. So here the model weights are actually public, and what's made private is a commitment to the data, and the data itself is hidden. And so this way, even though you have the output, you might still want to sell the prompt. For example, let's say that an advertiser wants to produce a variety of images for different demographics based off of this prompt. They can purchase the prompt and modify it for their own uses. Okay, so this is all I'll have to say about prompt marketplaces. Happy to take any questions up until this point. But if there are no questions, I'll also just happy to move on as well. Okay, I'll go ahead with the third application, which is trustless biometric identification and also finding deepfakes. But first, what exactly are deepfakes? I'm quoting here, a deepfake is an image or person, an image or video of a person in which their face or body has been digitally altered so they appear to be someone else, typically used maliciously or to spread false information. What I'm showing here is a fairly harmless example of a deepfake, but they're actually used in quite a variety of circumstances. So they've been used by state actors to spread misinformation, to trick businesses into miswiring funds, and also to scam unsuspecting consumers into going to websites, for example, like this, which I do not recommend going to because, of course, it's a scam. Now,
hello, everyone. As you know.
And they also even have a fake Sam Bankman-Fried voice along with it as well. Now, to fight deepfakes, we actually need a variety of technologies. And the first is what are these things called attested cameras. An attested camera has a trusted enclave on the device itself that signs photographs as soon as they come off the sensor. And because they're physically in hardware located next to the sensor, it's very difficult to perform attacks against these devices without physically having access to the camera itself. And because you have these digital signatures, you can basically prove that this camera took this photo, but say not this one, which is great. And very, very helpful, but there are many circumstances under which photo takers want to edit images privately. And so for one example here, we have this pig, which is stealing this credit card. You might want to censor out this credit card information before releasing it to the public. Similarly, if you want to do biometric authentication, you might want to crop a photo of your face and do it privately to do Face ID because you don't want to reveal your biometric information. So we developed a framework, zkImage, which attests to image edits securely and privately. And the way this works is that given a hidden input image, a zkImage will produce a zk-snark that this output image was derived from this input image. So going back to this F, if we take the functional view of image edits, the edit function takes an image as input and produces some output. And what's made public is a commitment to the input, and what's hidden is I meant to put the input and the output. The slide is slightly incorrect. Apologies for that. Now, of course, I mentioned that there are a range of technologies that we need to do to fight deepfakes. And so attested cameras and zkImage are a great first step. We also need other things. So for example, we need a registry where we have this original image that where the signature and hash are placed in the registry, along with any proofs of edits. And then when you see an image, if it comes along with a proof, you can verify that it's valid. So there's a couple of details in terms of testing to multiple edits. You basically need to split them up across multiple proofs if you want to do them efficiently. And the final application I want to talk about is Trustless Face ID. And for Trustless Face ID, given some original input image, what you want to do is first crop the image to focus on a person's face, and then do a Face ID model, which will then produce a proof that you have this chain from the attested camera all the way to the Face ID, and then this proof pi is made public. Okay, before I move on, I'm happy to also answer any questions about zkImage or anything I talked about so far.
Do you think the zero knowledge property is important here, or is it just to, prove that this came out of a camera / was edited?
So it depends on the application. If you are okay with revealing the original image, you don't need the zero knowledge property. But for example, for Trustless Face ID, if you want to do it in a privacy preserving way, you do need the zero knowledge property. So it depends on the application at hand.
I have one small question. Yeah, no, I'm wondering why, what kind of things you want to prove, and yeah, why it's violated? Because if you don't reveal the original image, you just reveal, okay, this image is taken by some attested camera, and what kind of image is it doesn't actually say anything. So I feel a little confused.
Well, I mean, in this particular example, what you've proven is that you've taken a photo of a face that matches the Face ID. So you can basically imagine logging into a service with Face ID, but doing it in a way that doesn't leak your biometric information. And so all this has to be done privately in order to preserve privacy.
Okay, thank you.
So as I understand, a lot of the value with attested sensors, right, is having a chain of data provenance from the point of capture to when it's used in the models. I think that sounds fantastic. I think it seems we need a little bit more infrastructure enforcement around that data provenance chain, right?
That's right. So you need this registry, for example. There's organizations, for example, C2PA, that are working on some of the other infrastructure that needs to be built around this. And so zkImage is one step in this process that needs to be done to fight deepfakes, and also do other applications like Trustless Face ID.
What's your take on how viable such a marketplace for prompts is? If we're looking at cases where the prompts are maybe kind of non-deterministic to the resulting image, right? So in Midjourney, you can put in the same prompt and get a different result different times. How does that affect sort of the value of proving a particular prompt and then trading it on a marketplace?
Yeah, that's a great question. So as it turns out, many of these, so as it turns out, ML computation is deterministic, and what changes is the random seed. So if the seed is an input to your ML model, it is actually deterministic computation. And so as a result, you can actually make this deterministic inside the zero knowledge proof. And so one method of actually producing edits essentially is to fix the seed and then change the prompt. I actually have some very visually compelling examples, but not on these slides. And if you shoot me an email, I can send them to you afterwards, where you basically have the same image, but you just change, say, Brad Pitt to Matt Damon or something, and then the image basically looks identical, except the face changes, more or less.
I will ping you then.
Great. Yeah, so as I mentioned, I'm happy to keep this interactive. If there's any questions, feel free to ask. I'll take a moment if anyone has any further questions.
Quick question. So for the prompt marketplace, what's kind of like the demand expectation there? Do you foresee people being interested in the exact same prompt, or more using that as an inspiration to tweak? And I'm guessing if like a batch of representative prompts would be really what would be interesting to people. Curious to get your thoughts on that.
That's also a great question. I will say that I'm primarily focused on the technology aspect, and in other words, enabling the feasibility of these from a technology perspective, because today you can't build these, period, without the technology that I'm working on. In terms of demand, it's very difficult to forecast, and I can speculate, but take everything I say with a grain of salt. None of this is investment advice, et cetera, et cetera. I suspect that given the pricing of these prompt engineers, you could imagine someone wanting to do this in a freelance way, and it's probably going to be cheaper than whatever this is. So if that's the case, there probably will be demand, but it also just depends on how much prompt engineering is a market outside of these decentralized marketplaces anyway. And for that, I don't have a good estimate on.
Thank you.
I guess maybe one way to think about it is that if you look at things like Fiverr or Upwork, there's definitely demand for that. But you also have full-time designers, but the type of work you do is slightly different. I think this is also going to be the case for decentralized prompt marketplaces as well.
I see. So you're saying you foresee sort of this is sort of like a resume building exercise, right? I have a portfolio of these prompts and like output proof pairings, right? And then I could do some other work for you as one potential use case to think about.
Yeah, absolutely. But same caveats apply, not investment advice. The future is hard to predict, et cetera, et cetera. Okay. So I'm going to go ahead with the rest of the talk, but again, feel free to stop me at any point. So I'm going to quickly walk through some of the evaluation for zkImage. And so here we use I believe this is an Intel instance, 64 threads and 512 gigs of RAM. And so we have a whole bunch of different edits here, which span things from cropping, resizing, to color space conversion, and also convolutions. As we can see, the verification is very cheap. So it's very cheap for any consumer of these things. But the proving is somewhat expensive. This is something that is going to go down with the advent of things like hardware accelerated proving and new advances in proving systems. And I also suspect that peak memory usage will go down as well. But even if you look at, say, the most expensive operation here, this is actually still feasible on a powerful Mac Pro. So you can do it on, say, a professional photographer's device, a professional photographer's editing desktop. Okay, so now I want to talk about the open source framework zkML that I've been working on over the past few months. So if you look at the zero knowledge proofs for data and inference, all the prior work focuses on these unrealistically small images, so unrealistically small data sets, for example, MNIST and CFAR10. And in this work, we scaled to ImageNet, which is widely considered to be production ready. And also things like GPT-2, MobileBERT, and even say the Twitter recommendation algorithm. Now, in order to produce zero knowledge proofs, we need to choose a variety of things, including the architecture, the optimization, and the proving system. So to optimize ENNs for zero knowledge proofs, we use quantized models. We optimize the layout in our framework, and we do it in such a way that we can achieve high accuracy. Now, roughly speaking, for the optimizer optimization, we use these polynomial constraints via linear layers. We construct the linear layers with these custom gates, which are these polynomial constraints. We do non-linearities via lookups, and we do a few 6-point arithmetic to make as a performance optimization. The code is fully open source. You can use it. And so, for example, if you want to achieve 99% accuracy on MNIST, it takes around 4 seconds to prove. In terms of the evaluation, so we produce a bunch of benchmarks on the mobile net version 2. And so as we can see here, the accuracy rate on ImageNet is around 79%, and the preprint that's online. But in the open source release, we achieve 10% higher accuracy, 6 times cheaper proving, and 500 times cheaper verification. So these numbers go down quite a bit. Now, to put this in context, what I'm showing here is the cost of verifying a private model accuracy. And with our open source release, these costs drop quite a bit. And so even the most expensive one here, say $415, this is compared to $85,000 for a moderate size data set. So I do have some slides on how this is done internally. I'm not sure if that's of interest to this audience. So I guess I'll do a quick poll. If you want me to talk about like a little bit about the circuit construction, please raise your hand in Zoom. Otherwise, I can just jump straight to the conclusion, and we can leave the last 10-15 minutes for free-form discussion. Okay, it looks like there's enough interest, so I'll quickly go through the circuit construction. Okay, so the first part of the circuit construction is these linear layers, which are very important. And the common operation that we use throughout is a dot product. And we have 2 gates for dot products. First is the actual dot product gate, and then accumulation gate, which is basically just a sum to accumulate dot products that don't fit within a single row. Now, given a dot product, you can reconstruct any linear layer, including matrix multiplication, convolutions, you name it. There's also a lot of nonlinearities that we have to use, including the ReLU, reciprocal square root, LU, GALU, the whole grab bag of nonlinearities. These can be done using lookup arguments. For shape operations, you can do things. Excuse me, these include things like padding, split, and concatenation. And because these only rearrange tensors, you can do this via copy constraints. And so they're relatively cheap. There's a number of what I'll call tricky operations, including the max, softmax, and variable division, which require special consideration. And I think these are basically the trickiest gate to construct in a high performance way. But beyond that, machine learning incorporates a bunch of other kind of tricky aspects, including how to represent floating point arithmetic, how to hide the weights. And so you have to basically, do these hashes within the circuit, and also things like optimal circuit layout, which all contributes to, are all required for high performance. But to conclude, we're increasingly interacting with digital systems, and zero-knowledge proofs provide trust in the face of adversaries. And this includes for ML models and also against deepfakes. Our framework is open source. The URL is down here. My email is here, and my Twitter is here if you want to contact me offline. But I still think we have around 10 minutes. I'm happy to take any questions, and free-form discussion or else would be valuable in the last 10 minutes.
Yeah, I'm curious about the floating point arithmetic, because usually you would use some finite field for the VK stuff, but I assume that wouldn't, for ML with SGP, that wouldn't really work, would it?
Yeah, so
Please continue.
Yeah, so there's some work on floating point arithmetic for zero-knowledge proofs. It's quite expensive. So instead we use these quantized models. And so basically, you can roughly think of it as switching floating point to fixed point, and then using that and using the fixed point representation instead of floating point representation. And fixed point is substantially cheaper to represent in computation in zero knowledge proofs. Does that answer your question about floating point?
Yeah, I have a following question about content. I mean, it's like if you have more bits, you actually should have more better performance. So I'm wondering, how many bits you need to get a good performance? I mean, would that be sensitive, let's say, from 8 bits to 16? So which part is what kind of bits should be the most cost efficient one?
Well, there's no answer to that question because it depends on the model. Some models you can get away with as little as four bits. Some models need 12 or more. It just depends.
Okay, and I assume that also the learning rate also need to be adjusted according to the bits you have, because according to my experiment, actually, if let's say if you set a very small bits, but with a very high learning rates, actually it doesn't provide you anything. It just go to the same value within a few training rounds. So actually, I think they are quite related with each other.
Well, typically, training is not really done in FP16, or sorry, in fixed point.
Oh yeah, okay, yeah, that's true. Forget me. I'm doing some online training things recently, so yeah. So yeah, cool. Yeah, thank you. Oh yeah, one more thing. I noticed that actually you can use a KZG and the IPA. So which kind of which specific proof system you are using?
Both. Halo 2 supports both. So you can just,
Okay.
I mean,
okay.
within our
Cool.
proving system, there's an option. You can just replace, like, so here we have KZG here, but you can just replace it with IPA. And then if you want a transparent setup, you can just switch it over.
Okay, cool. Thank you very much.
You mentioned got much faster verification than the benchmarks in the paper. How is that being achieved? So I thought you mentioned earlier that the verification is much faster than the benchmark you mentioned in the that's in the paper. Oh yeah,
Yeah,
this cheaper verification. So
yeah, so this is using IPA, which is also the one in the paper. But if you switch to KZG, the verification costs go down. Verification time goes down to like 5 to 10 milliseconds, which is exactly what you'd expect. So that's the reason why the cost goes down quite a bit.
Thanks.
Can you talk about the number of, like, say, the number of constraints and the number of advice columns when used for Halo 2? For example, for these for those benchmark times.
I don't have them offhand.
Like rough size.
Yeah, so for the mobile nets that I'm showing here, this is something like 2 to the 24 rows and like 30 columns, I think.
Cool.
If I remember correctly. But of course it varies depending on the mobile net. For the more expensive models like GPT, you need something like 2 to 26 rows and like maybe 30 to 60 columns, but I don't remember exactly.
Cool. Thanks.
Yeah, following this table, actually, I'm wondering what's the difference between actually some minimal parameters. After the mobile net, you have 0.35 and 96. What's the meaning of these two different parameters?
Oh, with mobile nets, you can have a different size mobile nets, and so the numbers after that just tell you the size of the mobile net.
Okay, cool. So so how many digits you use for quantization?
I think for this one we use something like 12 bits after the decimal or something. I don't remember exactly.
12 decimal bits. Okay, cool.
I think so, yeah.
Thank you.
This might be a bit of a long shot, but in practice, I think ML inference is also executed in parallel on GPUs, right? It's multi-threaded. So I wonder if you could essentially have multiple witnesses, each representing one thread on the GPU, and then you just have multiple proofs at the end of it, but you can very easily aggregate them. So it would be a cheaper, faster way of achieving similar results. What do you think?
Yeah, that would be cool. One of the problems though is that for a lot of these ML algorithms, there's often interaction. So for example, what's one common thing is this thing called a residual layer. We basically add the result of a previous layer to the next layer. So that can be quite difficult to split in zero knowledge proof because you need access to some of the previous witnesses. So I'm not entirely sure how to do it, but if there are ways that you can think of to do this, that'd be really awesome. I would love to chat offline.
I'll think about it.
So sorry, can I follow in this question? I think also that's very interesting. So would you like to give a more detailed description of your idea?
Me? This was literally just off the top of my mind. I mean, I've mostly worked with multi-level perceptrons myself, which are, kind of a basic architecture. And for them, I would imagine it should work. I'm not sure. I think I'm probably overlooking something though. But I mean, you can deterministically assign threads to the different parts of the computation, and then I would just imagine that would have sort of a bijective mapping to the corresponding number of proofs. I don't have a more detailed thought than that.
Yeah. I also